First question is, of course, how is my exam doing? Is it doing well? I'm sure it's doing well, resting, respiting from a hard day's work. Yes, that never existed. Turn on your cameras and let's begin the final struggle, the final climb. So today we speak about derivatives of inverse functions, inverse trigonometric functions to be precise. So tell me first question, guys. Do trig functions have inverse? Is sine of x invertible, please? Right, I'm saying we are talking about the derivative of sine inverse. Is sine x invertible? Please write in the comments. Is sine an invertible function? Very good. Inverse functions, guys, are not defined for sine unless you do what? Look at the situation. Here is sine. Yes? So this sine, if you look and you draw a horizontal line, the horizontal line intersects the curve at infinitely many points. Do you agree? Anywhere where you draw a horizontal line, when it crosses the graph of sine, because sine is periodic, there will be infinitely many points. And do you remember what is taking inverse? Taking inverse is the same as calculating undo. Right? So what was the input? If I take this y here, what input, when I ask for sine inverse of y, I'm asking for the input that produced it. Could it have been this input or this input or this input or that input? I cannot decide between those inputs. And therefore, sine is not an invertible function. Isn't that very simple? Now, what do you have next? If, on the other hand, you see this red curve, guys, if I restrict the domain of sine, here I write it with capital S. If I restrict the domain of sine, if I'm saying that the inputs had to come between minus pi over 2 to pi over 2, now the situation is very different. Now the function is invertible. So the global sine function isn't, but the restricted function is nonetheless invertible. Can you see that? So we define sine, capital sine x to be sine x where the domain is between minus pi over 2 and pi over 2. So now, guys, we would, of course, avoid using the capital letter S. We will simply say sine inverse and know that we mean the inverse of the restricted sign from this over this interval. Now, will you do me this favor? You will calculate right now what's the derivative of sine inverse. I haven't taught it, but we know the idea. Calculate the derivative of sine inverse to the best of your ability, please. We're looking for the derivative of the inverse function, as you can see here. Here it is. All right, guys, that should not take us too long, because what is sine inverse of x? We just say y equal to sine inverse x, which implies that sine of y is equal to sine of sine inverse x, which is x. You agree? Now, do you see what happens here, guys? In other words, I viewed that same curve from a different point of view. What is this? What is this describing? It describes me turning my head to the side and viewing the same graph from the y perspective. In other words, my up is now the x-axis. You see that? And if I view this graph of the inverse function where x is the vertical axis, then the graph looks like the familiar sine curve. And I know the derivative of the familiar sine curve. Here it is. So we have that cosine of y times y prime is 1, so y prime is equal to 1 over cosine y, which is 1 over cosine of sine inverse x. Are we in agreement? You see what I just did, right? So now what is cosine of sine inverse of x? I can evaluate this much better. I can simplify this formula. Look at it, guys. Here is a right triangle. Sine inverse of x is an angle. Here it is. It's an angle. Do you understand what it means, guys? Sine inverse of x means it's an angle that if you apply sine to that angle, you get x. Are you with me? Apply sine to this angle and you will get x. But x is this x must be the ratio of opposite over adjacent. Opposite over hypotenuse. So a simple way to do that is to write x here and 1 as the hypotenuse. There are other possibilities. You could have written x squared as the opposite, and then x would have been the hypotenuse. You could have written 2x as the opposite, and then 2 would have been the hypotenuse. All those triangles are similar. And so what happens here, guys, then the remaining side is root of 1 minus x squared. And so what is cosine? Cosine of this angle is adjacent over hypotenuse, and the result is simply 1 over root of 1 minus x squared. Yes? Everybody understood this, guys? You see what I did? In fact, the derivative of sine inverse is an algebraic function. That's pretty interesting. Now, if you followed my logic, please figure out, and very quickly, guys, I don't have time. You have 3 minutes to figure out cosine inverse derivative of that. Derivative of cosine inverse, please figure it out. Good, Moshe. John, the same. Very good. Very good, guys, if you figure it out. So let's see the same procedure applied here carefully. Y equals to cosine inverse x. That means that cosine y equals to x. At any point something unclear, let me know. Derivative of cosine is minus sine. So it's minus sine y times y prime equal to 1. And so y prime equals to 1 to minus 1 over sine y, which is minus 1 over sine of cosine inverse x. Yes? What is that cosine? What is that value? We can simplify it. We take this angle to be cosine inverse x. In other words, this is the angle. If you apply cosine to this angle, you get ratio x. So how do you get ratio x? You can say adjacent. Cosine is adjacent over hypotenuse. So adjacent can be written as x, hypotenuse as 1, and opposite is 1 minus x squared. Guys, when I write this, let me know for sure. Everybody understands, yes? You all understood how I completed this triangle and why that is very natural, correct? Cosine inverse of x is what? It means apply cosine to me and you get x. If you apply cosine to something, what can you apply cosine to? To an angle. Yes? To an angle. So cosine of an angle is going to be what? Adjacent to hypotenuse. And adjacent over hypotenuse is claimed to be x. That's what I do, right? So that's how I calculate this triangle. Now look at it. I need to calculate sine of cosine inverse. Sine of cosine inverse is just opposite to hypotenuse. So it's root of 1 minus x squared. And the result is minus 1 over square root of 1 minus x squared. So we now know how to take the derivative of cosine inverse. With that idea, guys, you are going to now calculate derivative of tangent inverse. That's a very important one. Nice. One more minute, guys. Faster. All right, let's do it together now. So what do you get, guys? You say y equal to tangent inverse x. Be careful. Now look what happens if I apply tangent. Tangent y is equal to x. So far everybody knows that, yes? You know what it means algebraically, you know what it means geometrically. Derivative of that expression is secant squared. Derivative of tangent is secant squared y times y prime, and that will be derivative of x, which is 1. So here we have that y prime is equal to 1 over secant squared y, which is simply 1 over secant squared tangent inverse x. Notice it's secant squared, guys. Yes? So what do we draw here a triangle? This is my tangent inverse x. And what do we get? So if that's my tangent inverse of x, guys, tell me, what do I write? Where do I move my mouse, my pencil? Here, here, here. Tell me what to write. Help me. Tangent inverse of x here is here. What does it mean? Well, thank you, Alexandra. So x is the opposite side and 1 is the adjacent side. Everybody sees this, guys? because apply tangent to this angle. Applying tangent means calculate ratio of opposite to adjacent. And the hypotenuse, just use Pythagoras theorem. So this is 1 plus x squared, square root, right? Square of the sum of the squares of the legs. Take the square root of that and you get the hypotenuse. But notice here, guys, so what is secant? Secant is, secant of this is hypotenuse to adjacent. So what do we get here? We get here 1 over the square root of 1 plus x squared. That's secant, and that's squared. Do you see why I squared it? Because I have secant squared as the derivative, right? So the result is simply 1 over 1 plus x squared. It's a tremendously important result. You can use that to calculate pi, for example. Yeah. For instance, guys, so are you interested in seeing how you can calculate pi, or you are beyond interested? Should I show you? Yes. All right, guys, you will help me see this thing. So tell me, please, what is the sum? You remember from the beginning of the semester. Tell me what is 1 plus x squared plus x cubed onwards, right? Tell me what is this equal to. Like, it's an infinite polynomial. Tell me what it's equal to. What is the full sum equal to, guys? I mean, we did it at the very beginning of the semester. It should take you seconds. No, not Jamal. No, not quite. Here is how you do it again, guys. I think you forget basic ideas. Yes, finally. This thing is a summation. Do you agree? The summation, right? So now what is that summation? It's 1 plus x times 1 plus x squared. Yes? You remember that from the very beginning of the semester, guys, the same idea. And that's what? So that's equal to 1 plus x times s, which means that if you move it across, you have that s equals to 1 over 1 minus x. Yes? Are you with me? This is, again, guys, I mean, we're going back. It's like, you know what is Sisyphean effort? It's when you are rolling a stone up the hill and it just rolls back down. Right? I mean, how many times do you want me to freaking roll the stone up the hill if, I mean, you're not understanding anything? So this is infinite series. Yes, it's S. And so look at what this means is that, guys, if I take 1 plus a number plus the number squared and whatnot, I get this. Now, can you tell me what will be then this expression, guys? If I want 1 plus x squared, what would it be? I want to reverse it, right? I begin with this expression, and I want to reverse it and make it 1 minus x squared. What do you think I need to do? Right? I want to, in other words, I want to go from here and I want to have this type of summation. Again, guys, don't focus on the x, right? So what is that saying? 1 over 1 minus a number will be 1 plus the number squared and onwards, right? So here is my number. So it's so what I want to do, I want to write 1 over 1 minus x squared. Do you agree? You follow why I'm doing it? I'm just putting it in that pattern. Again, guys, I know that 1 over 1 minus x is 1 plus x squared. Now, your problem is that you are focused on x, right? You're looking at the letters and you're not seeing the picture. What am I seeing? I am saying 1 over 1 minus a number is 1 plus the number squared plus the number cubed, etc. Yes? So to me, this expression is exactly the same. There is no difference. You see why there is no difference? Because I can write it as 1 over 1 minus a number. And then 1 minus which number? Minus x squared in this case. Do you follow? And so if that is the case, guys, tell me what should I write? What is the infinite expansion of that? 1 over 1 minus the number x squared. What should I do here? I should take 1 plus, help me please. What's the next term I'm adding? Of course. Look at it again, guys. Here is the box. Here it is. Where is that box here? It's over minus x squared. Yes? So what am I adding is minus x squared, exactly. So you see, you see what I'm doing. So it's going to be like this. So it's going to be, I'm going to draw the boxes. So you see that it's the same thing, hopefully. So it's this. Then it's going to be this squared. Then it's going to be this cubed. Then it's going to be this to the power of 4, and so on. And what do I put into that box? I put minus x squared, minus x squared, minus x squared, right? Minus x squared. So the result is that 1 over 1 plus x squared is the same as 1 minus x squared, and that would be plus x to the power of 4 minus x to the power, this is 2 times 3 is 6, plus x to the power of 8 minus x to the power of 10, right? Plus x to the power of 12, and so on. I'm just adding and subtracting even terms. Do you now see that? Because I just calculated it, right? So that's 1 over 1 plus x squared and onwards. You follow what I just obtained, guys? We're almost there. One more tiny little effort and you see that summation. But do you see it, guys? I'm not saying something incredibly insane, right? I mean, it's just, we did it already quite a bunch of times. You get it? All it takes is just not to pay attention to some x, not to be focused, but understand what you're reading, right? It's like when you're illiterate, you say I, B, R, A, or something, right? Or J, O, M, A, R. That's when you're illiterate. But when you're illiterate, you just right away read the word and take the meaning. So here is that meaning. Again, guys, 1 over 1 plus x squared in infinite form is what? It's 1 minus x squared plus x to the 4 minus x to the 6 plus x to the 8 minus x to the 10 plus x to the 12, and it goes forever. Good? It goes forever. Now, look at it, guys. This is the derivative of tangent inverse. Do you agree? I want to go back to tangent inverse. So, tangent inverse of x, guys. Can you guess, guys, if the derivative, so this is the derivative, right? So this is the derivative of tangent inverse, and the derivative of tangent inverse here, it created 1. What was the term here that created 1? What derivative? Derivative of what creates 1? Could you tell me? We're thinking in the reverse, right? 1 plus x squared is the derivative of tangent inverse is 1 over 1 plus x squared. Now, what should be the derivative? What should be here inside of this infinite parenthesis, such that when I take the derivative, I get this? What should be the first term? Can you tell me? Here, the first term is 1. What term was here that was differentiated and created 1? You follow what I'm saying? You think in reverse. What was that term? Can you guess? Exactly, x. X, derivative of x will produce 1. So this is x. What would have produced minus x squared? So we can say minus, what could have produced x squared, guys? Can you guess? If the derivative is x squared, what was the power? We have the power rule, right? So what was the thing that produced x squared? Oh, let's see. Well, clearly it's x cubed. Do you agree? X cubed, but if you drop it, it would be 3. So you need to write 1/3. X cubed, but times 1/3. You see, because the 3 drops down and it cancels, right? The next term is 1/5 x to the power of 5. You see why 1/5, guys? Because they take the derivative of that term. Here is what I'm saying. Here is the derivative here will produce this result. The derivative here will produce this result. Derivative here will produce this result. Yes? And then the next term is minus 1/7 x to the power of 7, and so on. Yeah, so basically you work backward. You understand? So what do I now understand? I now figured a way to represent tangent inverse as an infinite series. In other words, I figure out how to calculate using tangent inverse. See, I'm saying that tangent inverse x is x minus 1/3 x cubed plus 1/5 x to the power of 5 minus 1/7 x to the 7 plus 1/9 x to the 9, and so on and so forth. Yes? Now, guys, can you guess what value I can plug into tangent inverse to produce something related to pi? So do you know what is tangent inverse of 1? Tangent inverse of 1, for instance, is what? Tangent inverse of 1, in other words, what value do I plug in to tangent to produce the ratio 1? Tangent of what value produces 1? I'm asking, guys, tangent inverse of 1 is what? What is tangent inverse of 1, please? Pi over 4. You agree, guys? Tangent of pi over 4 will produce 1. You should know that. So this is pi over 4. On the other hand, tangent inverse of 1 is going to be what? It's going to be 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9 and so on and so forth, right? So then what do I see now? I see that if I multiply everything by 4, I see that pi is equal to 4 minus 4 over 3 plus 4 over 5 minus 4 over 7 plus 4 over 9 and so on, right? Then it would be minus 4 over 11 and so on and so forth. Yeah, plus 4 over 13, you know. So I just calculated pi. Isn't it amazing? And you see? Look at it. So if you carry out this calculation, you would get pi. Of course, actually convergence for this one, you would have to add a lot of terms. So it's not the thing that you use to actually come up with many, many decimals for pi. It's converging slowly. Very slowly, actually. But it is, if you add enough terms, you will get pi. You understand? All right, let's do another thing now. Tell me, please, what's the derivative of secant inverse x? Thank you, Moshe. Good. Yep, Aaron. All right, so guys, let's do it together. It should take you little time. So what do we have? We have here secant inverse of x is y, which implies that secant of y is x. And so the derivative is y prime equal to 1 over derivative of secant. Remember what it is. It's secant y tangent y. which is 1 over secant of secant inverse times tangent of secant inverse. One of those expressions are easily simplified. So secant of secant inverse is simply, they cancel each other. So it's x times tangent of secant inverse x. Agreed? And then to calculate this last expression, I draw myself a triangle. So here is the angle secant inverse x. That means that hypotenuse is x, adjacent is 1, and the opposite is x squared minus 1, square root. So I need to take tangent of that. So it would be root of x squared minus 1. So that is 1 over x root x squared minus 1. Yep. Not too difficult, correct, guys? I mean, what's there to make a fuss about? Or is it difficult? Now, let's before moving on, guys, just a quick verification. You see, compute, please, right? We all understand what is sine inverse. Sine inverse, it works on the interval. Well, the sign is restricted to the interval between minus pi over 2 to pi over 2 to make the function invertible. Please tell me what sine inverse of 1 is equal to. What's the first value equal to? Come on, guys, should be more than 2 individuals writing. You understand what this is saying, guys? So what do I mean about literacy? So if you see S, I, N minus 1 and 1, then you don't understand what it's saying. This is saying what value is mapped by sine, what angle is mapped by sine to be equal to 1. Do you understand? This means reverse. The output was 1. What did sine process? What was the input into sine? Yes? So the input into sine had to be pi over 2 in that interval. The answer is, here I'll write it here, guys. So sine inverse of 1 is pi over 2. Please tell me what is sine inverse of minus 1. Good, it's beginning to be fast. Come on, guys, 26 people here. Yes, minus pi over 2, very good. Now, sine inverse of root 2 over 2, please. Pi over 4. Pi over 4. Now please sine inverse of minus 1/2. All right. And the answer is minus pi over 6. You agree, guys? You should know. Remember, we spent 3 lectures, if not more, on trigonometry. I mean, I hope it was not for nothing. Now, sine inverse of minus root 3 over 2, please? What is that? There is a minus there, guys. Don't forget. It's minus root 3 over 2. Yep. Minus pi over 3. Right, I'm going to clear this. Last one, guys. Tell me, please, what is sine inverse of 5? What's sine inverse of 5? Come on. So far, I see only, what, 3, 4 people? Should be 23 people. And the answer is, of course, that this does not exist, right? There is no way to reverse, because such an input, such an output will never have been produced by sine, right? Sine is always a number between -1 and 1. Well, let me, of course, surprise you guys. That's only true for real numbers, right? So it's very possible to do that if you have complex numbers. So there is an answer, but that answer is imaginary or complex, right? So sine is extended to every single number. That's pretty interesting. I hope it's interesting, but not not for us. So if you were taking complex analysis, the answer will be not undefined. Right, guys, so this is those are the domains, the official domains for cosine x when it's restricted to be invertible, secant when it's restricted, tangent and cosecant, and I will not go too long into that. I want to move on. Right, guys, would you do me this last favor? I'm not gonna go through all those exercises. I want to move on. I have to. Please help me solve A, B, and C. All right, so what were we doing there? Okay, we solved problem A, correct, guys? Problem A should take us 2 seconds. Derivative is of the square is what? It's 2 tangent inverse x times the derivative of tangent inverse, which is 1 plus x squared. Done. Now do problem B, please. All right, problem B is also not particularly difficult, correct, guys? The derivative of tangent inverse of x minus root of 1 plus x is what? It's 1 over 1 plus x minus root 1 plus x squared multiplied by the derivative here, which is 1 minus x root 1 plus x squared. Yes? So we figured out B. Now, guys, please do question number C. Okay, maybe, why not? So do question number C, guys, 2 minutes. There is nothing sorry about it. Good, jump ahead. Derivative of C, please, fast. Let's in fact do it on a separate page. If you don't know the derivative of cotangent, derive it as well. All right, guys, let's do it together. So first of all, derivative of cotangent is equal to minus 1 plus t squared. Yeah, it's with a minus there. So the derivative here is minus 1 over 1 plus t squared plus what's going to happen here when I take the derivative. It's going to be minus 1 over 1 plus 1 over t squared, but the derivative of 1 over t is minus 1 over t squared. So altogether, what do we get? We get minus 1 over 1 plus t squared plus 1 over t squared plus 1. I multiply the t squared here, and the result is 0. Now, guys, before I move on, could you interpret this result? What does it mean? I took the derivative of a curve and I got that the derivative equals 0. It means what, please? Do you understand something about this function? It means this function is a what? The curve is constant, guys. Again, cannot emphasize that enough. Very important. Do you see, guys, what do we see? Even if I don't understand a curve, if I see that the derivative is doing what? It's analyzing the microscopic line segments like tiles, right? So here is a situation where the tiles, you see, the tiles are changing slope, changing orientation, so I don't have a line. Now, if the tiles are kind of like this, I will have a constant number for the derivative, like 5, right? If it's like this, could be 5. But if it's 0, it means it has to be like this. Slope is everywhere 0, which means my graph of this curve is constant. It's flat. Everybody says it. It's not only a line, but it's a line that goes parallel to my axis here. So it's a constant function. So this is the conclusion. Very important one, guys. Cotangent inverse of t plus cotangent inverse of 1 over t. It's simply a constant. Now, what is that constant? Let's try to understand what's that constant, guys. Let's look at cotangent inverse for a second of t. Okay, so if this is cotangent inverse of t, that means that adjacent over opposite is t. So this is t, and this is 1. This is pi over 2. What is this angle, guys, in terms of cotangent? Look at that angle, please. Tell me what is the angle in terms of cotangent. Well, the answer is very obvious, guys. The answer is it is cotangent inverse of 1 over t, right? In other words, this is the angle that cotangent would map to 1 over t. Are you with me? What is cotangent inverse of 1 over t? It means the angle that cotangent will map to 1 over t. If I take cotangent of this angle, this is adjacent, this is opposite. So it's 1 over t. So then what, please, if you understand cotangent inverse of t plus cotangent inverse of 1 over t equal to, what's the constant? Here is this triangle, look at it. This is an angle, this is an angle, what is it equal to? Come on, guys, more people should right away see it. Only 3 people? Guys, do you understand what it is? It's just a matter of reading and taking in the meaning. Right? Where all those things are just referencing to an angle by what the angles do. So what is this saying? This cotangent inverse of minus t is saying take cotangent of that angle and the result is t. Yes, so and why do I know that this angle can be named cotangent inverse of 1 over t? Because if I take cotangent of this angle, I will get 1 over t. Yes, so the result is that it's equal to pi over 2. Quick comprehension check. Guys, I want you to name this angle in terms of secant. I'm just checking whether you understand. Okay, but full sentence, please. The angle is named to be is what? So guys, what is the opposite side? The opposite side is root of 1 plus t squared. Do you agree? Yes? Now, what is this angle? If you take secant of this angle, you will get root of 1 plus t squared. So this angle is also secant inverse of root 1 plus t squared. So you also have this identity that cotangent inverse of t plus secant inverse of root 1 plus t squared will give you pi over 2. It's the same angle, I just gave it a different name. You also have this identity that this angle and this are the same, guys. You see that this angle and this angle are the same. It's very simply like, well, Lincoln, right? President Lincoln. It's also Honest Abe, right? Another name for him is Honest Abe. Another name for him is President of the United States during the Civil War. Yes? Those are all describing the same angle. That's just different names, different descriptions of the same exact thing. The rest you can calculate on your own. Now, guys, I'm going to talk about a useless lecture. Why is it a useless lecture? Because in my experience, no matter how much time I pour into that topic, people answer questions on that topic with probability that is close to 0. In other words, this is a difficult topic, and unfortunately, people are just not operating enough with their concepts to figure it fast. And nonetheless, I will try. I don't have too much time on it, and I will spend only maybe a lecture and a half on this particular thing, as I need to quickly move to integration theory, guys. So this is a very, very important topic in physics, and below I even include examples of how it's always used. See? The actual examples of where it's used, but for us, I mean, we're going to develop a very primitive machinery. Okay, guys, here is the situation. Imagine that you have recorded a YouTube video. And in that YouTube video, you are seeing, let's say, how a ship, a two-dimensional ship, is leaking oil. And because it's such a simple simulation, the shape of the oil leak is always a circular disc. And what you observe is that that circular disc is expanding at the rate of 2 square centimeters per minute. You understand? This red thing is expanding at the rate of 2 square centimeters per minute. That means as I move the time bar, the area of the circle becomes larger, and it becomes larger by exactly 2 square centimeters every minute. Now, there are several quantities that change here, guys. Do you see that this circumference? The circumference from time to time is different, right? It's getting larger. So the circumference is a function of time. By that, I mean that at any given moment of time, there is one particular circumference. At any given moment of time, there is only one radius. There are not 2 or 5 radiuses. There is exactly one radius. So it means radius is a function of time. What other functions of time do you see here? Well, the area, the diameter. Yes? What data changes with time, guys? And you can just see that circumference, radius, area, diameter are all functions that are directly controlled by time. But they are called related rates because the value of one of the rates is determining the value of another rate. So for example, if I know the radius, because I know the shape is a circle, I know the area and I know the circumference. And if I know the area, I will know the circumference. And if I know the area, I will know the radius. Do you understand? So they are related. So even though radius is of one function of time and area is another function of time, there is obviously a relation between them. And here is that relation, guys. A of t is pi r squared. You see, A of t is pi r of t squared, because area is always the square of the radius times pi. Agreed? Circumference is 2 pi times the radius of t. And it's also, circumference is also pi times the diameter of t. And area can be written as circumference squared times 1 over 4 pi. I can relate one quantity to another, hence the term related rates. Now, guys, you are going to try to help me see if you have an intuition for this type of thing. Here is now the tanker question. Suppose the tanker is leaking oil at a rate of 2 meters squared per minute. I would like you to tell me first intuitively, guys, the radius, right? The radius is growing. Nobody doubts it, right? Leaking, so the stain is getting larger, the radius is growing. Now, is the radius growing at a constant speed? Is it speeding up or is it slowing down? Please write in the comments if you see that. The radius, as the leak is expanding every minute, the area of it is expanding by 2 square centimeters. Is the radius growing faster with time, speeding up with time, slowing down with time, or staying at a constant rate? Okay, so let's see. The problem, I said the rate of the growth, I said centimeters squared, guys. You know, so the area is growing. Do you agree? Is the radius speeding up, slowing down, or staying or growing at the same rate? The radius is also growing at a constant rate, you're saying. So how many of you are in consensus that the radius is also changing at a constant rate? Okay. Yes? Is that your consensus? Don't agree on consensus because you're wrong. How would the radius be? Just think about it, guys. Area is growing. What does it mean that area grows at a constant rate? It means that in 1 minute, if I begin the experiment in 1 minute from the beginning, I will have twice 2 centimeters. And then in 2 minutes, I will have 2 plus 2 square centimeters, 4 square centimeters, and then 6 square centimeters, 8 square centimeters, right? You see that, guys? Now, let's see what happens if the radius doubles, right? So each time the area, we say, how long does it, what happens if the radius is doubles? If the radius is doubles, the area quadruples. You agree? Because it's r squared. You see? So what do you think? I mean, here is the time that it takes the radius to double. Now, if you double the time, are you claiming the area will double? Because area will double with time, right? Take this amount of time, you get some area. Double the amount of time of, then you get double the area. Are you saying that if you double the amount of time, you'll get double the radius? If that's the case, then the area would be quadrupled. That means that the radius must slow down. And do you understand, guys, what we're going to try to calculate? I personally imagine that at the edge of the radius, there is a speedometer, and the speedometer is riding there as the radius expands, and the speedometer shows the exact velocity of the radius at any given moment of time. Good? So let's try to carry out some calculations, guys. If the video, here is that video, right? Remember, area grows at a rate of 2 square centimeters per minute. If we begin the video from just when the leak began, when the area was 0, I would like you to tell me explicitly, give me an explicit formula for A of t, for the area in terms of time. Could you do that? What's the area in terms of time if the video begins from the start of the leak? Let's look at it, guys. Time is 0. How much area do we have? Time is 0. How much area? 0. If I begin it when the stain was not there yet. Time is equal to 1. How much area do we have? Time is equal to 1. Area is 2 times 1, yes? Time is equal to 2 minutes. We have 2 times 2 minutes. You agree? Because 2 minutes, it's 4. So what's the relationship to time, guys? It's very simple, 2 times t. Yes? 2t. Now, could you tell me explicitly what is the formula for the radius in terms of time? So area of t is equal to 2t. Please tell me what's the radius as a function of time. Very good. So here are the solutions to that, guys. So you see, area is 2t. If at 0 time I have 0 area, and radius then will be root of at over pi. Because why? Because a is pi r squared. So to solve for r, I just take this quantity, that's a, divide by pi and take the square root. Do you agree? So the formula for the radius explicitly is root of 2t divided by pi. And now let's, guys, I am interested in, so you see what happens here, guys, yes? So this is changing as a root. It's not linear. You see that this one is linear, but this one is not. It's slowing down. If you double t, the growth is by a factor of root 2, which is not 2. Yes? Root 2 is smaller than 2, so it should slow down. Now let's explicitly see what's the change, what is the speedometer showing. Do you remember, guys, that speedometer, you remember that we started talking about derivatives as representing change of distance over change in time. Yes, why? And we would take the difference in time to be very small, so that it's essentially evaluating a constant velocity, because in a small interval of time, acceleration will not have any effect. That's the philosophy. So therefore, we calculate r prime of t. Derivative of r of t is root of 2 pi times root of t. Derivative of that is this number. And 6 minutes into that video, it's root of 2 pi times 1 over 2 root 6. Yes? So that's my, I mean, I can easily figure out the speedometer function for the radius. And at 6 minutes in the video, this is the speedometer, what the speedometer is showing. Simplify it, and you get a sort of number that the speedometer is showing. Now I can also carry that calculation implicitly. You see, A of t is equal to pi r squared. Yes, guys? That's the related rate part. So I suppress the t so that it's easier to write. I just write A equal to pi over pi r squared. Now you see, guys, I actually obtained formulas for A and I obtained formulas for R explicitly in terms of time. But in general, that is very difficult and not convenient. Even if I could do it, it's usually not convenient. So I take the derivative with respect to A using implicit differentiation, that's the A dt. And the derivative on the other side with respect to t is pi 2r dr dt. Now what do we get here? It's 2. And the derivative here is 2 pi r dr dt. Now I simplify, I move everything around to say, to just, you see why it's 2, guys? Because the area is changing at a constant rate. So what do we get? We got that the r dt is 1 over pi r. And if t is equal to 6, I mean, I will get the r dt equal to this quantity. In other words, guys, I can obtain this dr dt as an implicit differentiation formula. Notice mathematically that this video was very simple. I mean, we describe a ship that's leaking oil, but that's entirely not important. What's happening is that you have a circle growing, right? Really, what is it mathematically? It's a circle that's becoming larger, nothing more. Yes? Now, tell me, please, guys, with the next problem. So we have that air is being pumped into a spherical balloon. So we have a sphere that's growing, right? And the air is being pumped so that its volume is increasing at a rate of 100 cubic centimeters per second. So what does it mean? In each second, the volume is containing extra 100 cubic centimeters every new second, right? In a half a second, it will contain extra 50. You understand, guys? Right? So it's uniform. It's uniform in such a way that in 1 second you get extra 100. Now, I would like us to figure out how fast is the radius of the balloon increasing when diameter is 50 centimeters. Diameter, guys. Now, for that question, you might find it useful to know the formula for the volume of the sphere. The volume of the sphere V is 4 over 3 pi r cubed. Now, can you try to figure out this question? I'm going to come back in a few moments and we'll talk about it. All right. Wakey, wakey. Let's do it together, guys. So what's really happening here? Could you please help me with at least the imagery, guys? What is happening in my YouTube video? Mathematically speaking, right? I mean, all the other things are not important. A bit about the area. Well, first of all, volume, and secondly, what really is happening is you are seeing a larger growing sphere. Look at it. In the first video, we saw a growing circle. Now we're seeing a growing sphere. Yes, guys? Now here is that YouTube video. You see? And we are going to move time. We're only interested in the speed of the growth of the radius when the radius is equal to 25, right? Diameter is 50, that means radius is 25. So you see, I track the radius until it grows to 25. I pause the video there. I want to know what is the speedometer on R showing. Can you imagine there is a speedometer? That's what I personally think, is that there is a speedometer attached here. Okay, and I just want to read what it's saying. So here we go, guys. So R of t is R, and I'm pausing when it's 25. So V is 4/3 pi R cubed. Why do I need V? Because I'm not interested that right now to calculate the explicit formula for how R is changing, but I want to know the speedometer, and only at one point here. So what do? I take the derivative of V with respect to t, and the thing that V is equal to with respect to t. I get dv dt equal to 4 pi R squared dr dt. What is dv dt? It's 100. And on the other hand, when I take derivative here, it's 4 pi R squared dr dt. Yes? Now, what is that, guys? So all I have to do is I have to divide 100 by 4 pi R squared, and I get 25 over pi R squared. Now R is equal to 25. So that means that the R dt at R25 is 1 over pi times 25. This is my growth of the radius when R is 25. Let's do one more example, guys. We'll do that maybe together as we are short on time, but you will help me. Guys, a ladder is 10 feet long and it's leaning against a vertical wall. Imagine my arm here, right? Leaning against a vertical wall, and then the bottom of the ladder is pushed away from the wall at a rate of 1 foot per second. In other words, it's constant. You see this is what's happening. Constant, right? You see that, guys? Now what's happening to the top? You can see that the top, guys, here, you could not see the tip of my fingers, but now suddenly you can see my full hand. The top is coming down along the wall. Yes? Here it is, guys. Here is the wall. Yeah? So the question is, how fast is the top of the ladder sliding down when the bottom of the ladder is 6 feet away from the wall? Now help me please with the following, guys. What am I seeing? What animation am I really seeing? In the first video, I saw truly just a growing circle. In the second video, I saw a growing sphere. What am I seeing here? Moving line, but more so a right triangle, right? It's more useful to think of it as right triangle. Because look at it, guys, here is that video. Do you see here is the ladder? The hypotenuse of the triangle is the same, but x and y are changing, right? Initially x is 0 and y is 10, and then y is getting smaller, x is getting larger as I move in the video. But always together with the wall, I see x and y, I see a triangle, a right triangle. Yes? So my goal is to relate the motion of y to the motion of x, the related rates. What's the nicest, what's the relationship between x and y, please? Could you tell me how can I relate y to x? Y is decreasing, x is increasing. How can I relate between them, please? Yes, that's a very interesting idea. You can use tangent. I like it. Yes, so tangent is a possibility. In this particular case, because I know the ladder is 10 feet long, it's better to use Pythagorean theorem. But I like that you mentioned tangent. It's very nice, right? You try to avoid the ladder, but the ladder is not growing. So here it is much better to use, more efficacious, I think they call it, to use x squared plus y squared equal to 100. So that's what we're doing, guys. I accidentally did not write the extra zero. It's x squared plus y squared equal to 100, and I know that dx dt is 1. So when I take the derivative with respect to t, I get 2x dx dt plus 2y dy dt equal to 0. And when I move things around, I see that, look at it, just move whatever is multiplying. I just take 2x dx dt, and I move it across, and I get minus 2x dx dt, and then I divide by 2y, so I get minus x over y dx dt, and dx dt is 1. So the result is that dy dt is just minus x over y for all values of t. Now I am in particular interested where x is equal to 6. So if x is equal to 6, I use Pythagorean theorem. So what is y? Y is root of 10 squared minus 6 squared, which is the root of 64, which is 8. So the result is minus 6 over 8. You see, x is 6, y will then be 8 by Pythagoras theorem. So it's minus 6 over 8 feet per second. And that is minus 3 over 4 feet per second. You understand? I mean, I can go slower afterwards in office hours, guys, but again, slow or fast, you have to struggle with those questions because, you know. Now, here is another one. A water tank has the shape of an inverted circular cone with base radius 2 meters and height 4 meters. If water is being pumped into the tank at a rate of 2 meters cubed per minute, find the rate at which the water level is rising when the water is 3 meters deep. Again, guys, here is the video. First of all, the volume of a circular cone is 1/3 pi r squared h, where h is the height of the cone, r is the radius of the base of the cone. Now, in this video, do you see, guys, that what you truly are seeing is one small cone growing inside a bigger cone? They are proportional. You agree? I mean, again, you see, we're seeing basic shapes changing, right? We saw right triangles changing, we saw circles changing, we saw spheres changing. That's pretty much how you reduce it in your mind. And here we are seeing cones changing. Now, guys, I have r. R is a function of time. This is r. And the depth h is a function of time. But I do not want r. I don't need anything about r. I just want, I know how fast is the volume changing. That is 2 cubic meters per minute. I do not want to figure out how much the radius is changing. So what do I do, guys? I do the following. Look at it. Do you see that the triangles here are similar? So 2 divided by 4 is the same as r divided by h. They are proportionally the same, right? So this is just a smaller, a miniature copy of the big cone. So 2 over 4 will be r over h. Right? So that means r over h is 1/2, and r is equal to 1/2 h, which I immediately plug into my formula. So where I saw r, it's 1/2 h squared. Now that was r squared, now it's 1/2 h squared. So when I simplify it, I see that my volume just in terms of h is 1 over 12 pi h cubed. Are you still following? Make sense? Proportionality, yes. Radius over the, yes. Pythagorean theorem, maybe why Pythagorean theorem? I mean, just r over h, 2 over 4. Same thing. So then we take the derivative. dv dt is 2. Derivative here is 1/4 pi h squared dh dt. And everything else is just a calculation, guys. Everything else, I mean, h is 3. I'm told to estimate when h is exactly 3, how fast is it growing? So I plug in 3 into this formula, and I get 8/9 pi meters per minute, which is 0.28 meters per minute. One more question and we are done. Any questions before I continue about the previous problem, or too many questions you don't know what to ask? A man walks along a straight path at a speed of 4 feet per second. The Gesundheitsgestapo searchlight is located 20 feet from the path and is kept focused on the man to make sure he is a good citizen. Like this. That's 20, right? At what rate is the searchlight rotating when the man is 15 feet from the point on the path closest to the searchlight? So when x is 15. First question, of course, guys, do you know what is Gesundheitsgestapo? No, but you will know very soon. Don't worry about it. Just wait a little longer. I'm not from me, I'm saying. I mean, you'll know it in life. So what are we truly seeing here, guys? We're truly seeing here this. This is the camera. It's located here. It's rotating to keep the person in focus. The person is walking along the wall at a constant rate, and the closest point to the camera is here, 20 feet away. Well, almost. It's a Nazi police, but not. But there is another word you miss here. So we have this this distance. So what happens here, guys? What do you see? X is increasing at a constant rate of 4 feet per second. The man is walking at 4 feet per second. You see, so what the movie is really about, it's about a right triangle where the hypotenuse is getting longer. It's not quite the ladder triangle because the hypotenuse will eventually be here, then here. You see what I'm saying, yes? So what's the nicest way? We are only interested in relating the angle theta to X. Can you figure out, guys? I want to relate the angle theta to X. What's the nicest way to do that? What's the easiest way to do that here? All right, good. Good. Tangent is the nicest way to apply here, guys. So tangent of this angle will right away make it x over 20. So I avoid using the increasing hypotenuse because it's also changing as time, and I only want the angle to be related. So that's the first major aspect, guys, which you have to figure out how to do in solving those problems. Tangent of theta is x over 20. I take the derivative with respect to time, you get secant squared d theta dt. I want to know d theta dt, how fast is this rotation happening? Equal to 1 over 20 dx dt, which is 1/5. So that means d theta dt is 1/5 1 over secant squared theta, which is 1/5 cosine squared. Now I pause when x is equal to 15, guys. What is cosine squared? Look at it. Cosine squared is the square of the ratio of 20 to hypotenuse. So when I square it, it's 20 squared divided by square of the hypotenuse, which is 15 squared plus 20 squared. And the answer is, when you simplify on the bottom, it becomes, when you simplify factor out, you just get 16 over 25. And so you multiply that by 1/5, and you get that the camera has to rotate at a rate of 16 divided by 125 radians per second at that moment, which is 0.128. Now, whatever follows, guys, I'm not sure if I'll explain it in class, but it's highly important, highly useful, and highly complicated. This is related rates applied to mechanics and physics. Right? This concept is, you use it in physics every single time. Okay, so when you think right away application of calculus to physics, this is immediately the first thing you encounter. And at that, I wish you goodbye, unless you want to stay and talk in office hours about something, or watch a question from What, When, Where, or something else like of the sort. If that's not your wishes, then take care, guys, and be warned that time is running short. Next week, Thursday? Why is next week, Thursday, our last class? When is our last class? I don't know. I think it's the 19th or something, right? But I mean, if you want to, we can never part. We can stay here, because have we learned the material? No, I don't think so. We haven't, right? So where are you hurrying?